Hello, my name is Gurumurthy Ramachandran, and we are continuing our discussion of uncertainties in physical measurements. In this section, we'll be talking about uncertainty and its propagation. So, before we get into that, we need to discuss two concepts, namely random and systematic errors. And so, on the right hand side, there is a figure that shows a series of measurements of some physical variable, and on the y axis are the actual measured values. And so, when we talk about uncertainties, there are two types, random and systematic. So, the uncertainties in a measurement system that can be revealed by repeating the measurements are called random errors. And so, in the figure on the right hand side, you see on the top a dotted line, a dotted horizontal line with a scattering of measured values that are shown by the diamonds, black diamonds. And so, each black diamond is an individual measurement with a certain value assigned to it. And they are clustered around this horizontal dotted line, which is some kind of an average value of those measurements. And so the variability in those measured values is called random error. And this is the scatter around the average value. And we can calculate that, as we'll discuss later on, using statistical methods. So that's random error. In contrast, systematic errors are those that cannot be revealed by repetition. And so for determining systematic error, we need a different measurement system that gives us an independent estimate of this known value, of this parameter. And so this is denoted in this figure by a line at the bottom, which is a horizontal line marked as the known value. And so the known value is known independently of this measurement system that we have right now. It is known from a different measurement system. And the difference between this known value and the average of all our measurements is called the systematic error. If our measurement system were really good, then the systematic error would be very, very small. But otherwise, there is a big, fairly significant amount of systematic error. And as I said before, this systematic error cannot be determined by repeated measurement using our own measurement method. We need an independent source of information for determining systematic error. Also, a couple more terms. So the random variability, the scatter of these values around the measured average value, is called the precision of the measurement system. And the difference between the average of these trials and the true value or the true known value is known as the measurement bias or systematic error. So let's start off with some simple examples. So let's say we used our rotometer that we discussed earlier, and we made repeated measurements of the flow rate of air through an air sampling instrument such as the rotometer. And we made 4 measurements in liters per minute. And these are 28.3, 28.2, 28.4, and 28.3. Without doing any kind of statistics, given these 4 values, we can make a reasonably safe assumption that the best estimate of the flow rate is the average of these 4 values, that is 28.3 liters per minute. Another safe assumption is that the correct flow rate is between the lowest value, 28.2, and the highest value, 28.4. So if we know the precision of the measurement, then the best way to report the result of a measurement is to give the best estimate of the quantity and the range within which we are confident that the quantity lies. Thus, if we are measuring some variable x, then the measured value of x is the best estimate of x plus or minus some error, which is denoted by delta x. This implies that our best estimate of the quantity of interest is x best estimate, and we are reasonably confident, and we'll talk more about what we mean by reasonably confident later. We are reasonably confident that the quantity lies between x best estimate minus delta x and x best estimate plus delta x. And the number delta x is the uncertainty or the error, or also called the margin of error. Now we can talk about the propagation of uncertainty. So most quantities of interest in industrial hygiene or exposure assessment cannot be determined in a single measurement, but are found in several steps. We measure several quantities that can be measured directly, and then the quantity of interest is calculated using these measurements. So, for example, when we want to find the concentration of some chemical in the air in a workplace, we measure the mass of the contaminant that is collected on some medium. The mass is lowercase m, and the volume of air that we have sampled is capital V, and the concentration is m divided by V. So if m is in milligrams and V is in cubic meters, then the concentration will have units of milligrams per cubic meter of air. Now, the volume of air is determined using two other measurements, which is the flow rate of air, Q, and the sampling time, T. And so if Q is in cubic meters per second and time is in seconds, then the volume has got units of cubic meters. And so you see now that the concentration requires three separate measurements. One is mass, which for the m over v, and we need the measurement of flow rate in cubic meters per second or cubic meters per minute, and time, which is in units of seconds or minutes. So three different measurements, mass, flow rate, and time, are needed to calculate the concentration. So when you have a measurement that takes several steps, three in this case, then the estimation of uncertainty also involves several steps. So in this example, we have to estimate the uncertainties in the quantities measured directly, namely mass m, flow rate q, and time t, and determine how these uncertainties, quote unquote, propagate through the calculations to produce an uncertainty in the calculated concentration. There is a well-known theorem in calculus that we'll use to determine this uncertainty in our dependent variable, which is the concentration. So in the most general case, let's assume that we are measuring several quantities, x, y, z, and so on, each one with an uncertainty delta x, delta y, delta z, and so on. And the quantity of interest is f. And f is a function of x, y, and z. And we need to estimate the uncertainty in f using the uncertainties in x, y, and z, namely delta x, delta y, and delta z. If the uncertainties are independent and random, then the uncertainty in function f is given by this equation that follows. Delta f, which is the uncertainty in f, is equal to the square root of delta f divided by delta x times delta x squared plus delta f divided by delta y times delta y squared plus delta f divided by delta z times delta z squared. And so in this equation, delta f over delta x, delta f over delta y, delta f over delta z are the partial derivatives of f with respect to x, y, and z. And what it means is that delta f over delta x is the derivative of f with respect to x while we keep everything else constant. We are assuming that y and z are constant. Likewise, delta f over delta y would be the derivative of f with respect to y, keeping x and z constant. And delta f over delta z is the derivative of f with respect to z while keeping x and y constant. So how do we apply this equation to our problem? So in our example, we're drawing air through a filter for a certain amount of time at a given flow rate and weigh the mass of dust collected on the filter. And we are then going to calculate the dust concentration. So the concentration of the dust is obtained as C equal to mass of dust M divided by Q, which is the flow rate of air through the filter, times the amount of time that we are doing this sampling for. So M divided by Q times T. In this case, we have these three variables, M, Q, and T. And so we can find out the partial derivative of concentration with respect to mass, which is just 1 over Q times T. Then the partial derivative of concentration with respect to Q is minus M over T times 1 over Q squared. And the partial derivative of C with respect to T is minus M over Q times 1 over T squared. The uncertainty in the concentration is therefore calculated by using the equation we had in the previous slide. So the delta C, the uncertainty in concentration, is the square root of delta C over delta M times delta M squared plus delta C over delta Q times delta Q squared plus delta C over delta T times delta T squared. And we can then say, okay, I'm going to divide both sides by concentration, C, and it will give us the fractional uncertainty in C, which is delta C divided by C. And after some manipulation, which I'm not going to derive in detail, we arrive at this equation at the bottom of this page, which is delta C over C is the square root of delta M over M squared plus delta Q over Q squared plus delta T over T squared. In other words, what is on the right-hand side under the square root sign is the sum of the squares of the fractional uncertainties in mass, flow rate, and time. So let's put some numbers to our equation. So let's say we measured mass as 24 plus or minus 2.3 milligrams. And the flow rate, we said we measured it to be 2 plus or minus 0.1 liters per minute. And the sampling time was 480 plus or minus 5 minutes. Then the calculated best estimate of the concentration is best estimate of the mass divided by the best estimate of flow rate times the best estimate of time. So it's 24 milligrams divided by 2 liters per minute times 480 minutes. And in this case, you see that the liters per minute has been converted into cubic meters by multiplying it by 10 to the minus 3. So 2 liters is 2 times 10 to the minus 3 cubic meters. And so the best estimate of concentration is now 25 milligrams per cubic meter. The fractional uncertainties in the measurement of mass, flow rate, and time are, for mass, we say it's 2.3 divided by 24, or 9.5%. For the flow rate, it is 0.1 liters per minute divided by 2 liters per minute, that is 5%. And for sampling time, it's 5 minutes divided by 480 minutes, or about 1.04% respectively. And so the fractional uncertainty in the estimate of concentration is you take the square root of 2.3, which is the fractional uncertainty, or which is the uncertainty in the mass, divided by 24, plus 0.1 divided by 2 squared, plus 5 divided by 480 squared. And you take the square root of all of this, and you get to around 10.8%. And so that's the fractional uncertainty in our estimate of concentration, given that there's uncertainty that we have quantified in the measurement of mass, flow rate, and time. And so that's the fractional uncertainty. And the actual uncertainty is you multiply that 10.8 by the best estimate of concentration that we obtained above, which is 25 milligrams per cubic meter. So 0.0108, so that's 10.8%, times 25 is 2.7 milligrams per cubic meter. Thus, we would report the result of our measurements as the best estimate, which is 25, plus or minus the uncertainty, which is 2.7 milligrams per cubic meter. So anytime a measurement is made and you have to report its results, this is the format in which the results should be reported, namely the best estimate and the uncertainty in your estimate. Without an uncertainty estimate, it's basically wrong. You cannot report a measurement without reporting the uncertainty in it.